Last time, we worked through a very important example, which taught us key lessons that we are going to use to understand the use of magnetic fields in circuits. This particular circuit that we were analyzing, you will recall, featured a spatially constant magnetic field. It's the same everywhere in space. It's some externally imposed magnetic field on this system. So it doesn't have to be just located inside this solenoid. This is just some external field imposed on our system. It's constant throughout space, but it is a function of time. And in particular, we were considering the case where it is an increasing function of time. And then what we did, so as to harness that magnetic field into a circuit, is that we employed a coil, as I've sketched for you here, and then wired that coil in such a way that it has a magnetic flux going through it, and then it's connected through an external ideal wire through a resistor R. There are various parameters in this example, of course. The coil, or solenoid as it's sometimes called, had a cross-sectional area A. It had N turns total, and the number of turns then per unit length, lowercase n, was equal to the total number, capital N, divided by L. So this should really just say N turns, not turns per unit length. N turns, turns per length is this lowercase n. Now, in terms of an analysis, we were performing basically our standard circuit analysis. What we had done to enable us to do this was to modify or just look at Faraday's law actually slightly differently. I've moved the minus sign here onto the other side of the equation. You will recall there's always an opposing minus sign due to Lenz's law. The reason why I'd like to arrange it this way is that the minus the integral of E dot dl around a closed loop is what we always refer to as the sum of the voltages. But now, the sum of the voltages don't quite give us zero, as we are used to thinking, because there is this additional flux term, time derivative of flux term, that appears on the right-hand side of the equation. So what we really have, along with this change in the integral of E dot dl, is we have a new Kirchhoff's law that's just modified by the presence of this additional flux term. We then carried out our standard Kirchhoffian analysis, but included this additional term. In particular, we decided to go around a loop through our circuit in the direction I've indicated by this outer arrow, and that loop takes us then through all of these wires throughout our circuit and our resistance. Beginning with the resistance and going in this direction, we decided to make our presumed direction of current in the direction I've indicated to you here. That actually turned out to be an incorrect guess, but at least it establishes a sign correction, a sign convention for us. And under that sign convention, this is the positive or upstream side of our resistor, and this is the negative downstream side. So as we move along then and go through the resistance, we have IR, but we're going downstream as we loop here around our Kirchhoffian loop. Going downstream, that's minus IR, plus then we have the integral of V dot dl as we go through our wire. But this is a stationary wire, which has always, and it's ideal, so it always has exactly zero electric field inside. So the rest of this voltage change throughout this wire is actually zero. The effect of the solenoid comes in through the magnetic flux term. So we had the time derivative, and then we evaluated the magnetic flux, which is calculated here for you as follows. There are n turns here, and each turn has an area A. So each turn gives a contribution. So we multiply the total flux. To calculate the total flux, we multiply by the factor n. Then we're left with the integral of B dot dA, which of course gives us the magnitude of B, which we're calling B of t. The magnitude of dA when integrated across one of these surfaces just gives us the total area A. And then finally, we have the cosine of the angle between area A and magnetic field B. And this is where our right-hand rule is very important to establish the signs. In this case, the direction that we are going around our loop is determined by how we're following Kirchhoff's law. We're going around our circuit this way. That means we are looping around as so through the solenoid. We're coming across this direction in front and back to the left and back, and then comes down around here, back across in front, and to the left and back, and so forth as we go down our solenoid. What this means by right-hand rule 2 If you curl your fingers in this direction, your thumb then points straight up, and that establishes the normal vector, or dA, for each of the particular surfaces. And that normal vector happens to point in exactly the same direction as the magnetic field for these cases. So the angle between the magnetic field and the dA vector is 0. That gave us this factor of cosine 0, which we then can determine to give us a 1. Now these are all the key components in our analysis that we need in order to establish, in fact, the behaviors of a new type of circuit element known as a solenoid, which occurs when actually what we do is not depend upon an external field, but in fact just depend upon the field that is generated by the current going through the coil itself.